I suggested in my previous video that one of the benefits of representing functions as power series is that the math or the calculus is way easier when we're dealing with polynomial terms than it is often with the function itself. So to explore this idea, let's take a look at a function, in this case 1 over 1 plus x. And let's just do a couple of quick operations or manipulations to it so we can start looking at the power series. So for example, f of x is 1 over 1 plus x. Let's just ask ourselves real quickly, what's f of x squared? Well, we know that 1 over 1 plus x, right, would simply be 1 minus, well, let's go backwards actually. Let's look at what f of x squared is first. And all that means is to substitute x squared in for our argument x. So this would be 1 over 1 plus x squared. Then let's look at f of root x or radical x. And this would just simply be 1 over 1 plus root x. So then if I ask you to write the power series for f of x, we know that since this here is our first term, a, and this here is our common ratio, r, we can then just write the following. We'd say this would be 1, and then, oh, I should say this here, we should be very clear, I apologize. This here would be 1 minus negative x. So our common ratio is actually negative x. So this series would look like 1 minus x. And now we're going to multiply this negative x by a negative x. So that's plus x squared minus x cubed. And this is just going to keep going. It's going to alternate back and forth with the signs. Now, using this power series that I've just written for 1 over 1 plus x, let's write the power series for 1 over 1 plus x squared. Well, all that really means now is we are going to substitute x squared in for each one of these terms. So we're going to say this first term would still be 1, but this next term now would be minus, and instead of just x, we're subtracting in x squared. This next term now would just be x to the 4th minus x to the 6th. And you might be asking yourself, wait, couldn't I have just rewritten this denominator so it would be in the form of 1 minus r and done the same thing? And the answer is yes. And these are pretty basic examples right now. But just to really get the idea that we can leverage what we know about the power series of 1 over 1 plus x, this similar function, to write the power series for 1 over 1 plus x squared, that there is a connection there. Similarly, if I wanted to do this for 1 over 1 plus root x, I could just say, all right, well, this would be 1 minus, and now we're substituting root x for our argument or variable x. So this would be 1 minus root x plus x minus x root x, or you could also write this as x to the 3/2 if you wanted to. Okay, so on that note, kind of following along in the same vein, let's see if we can come up with power series or use the power series from this example here to find the following power series. So start with g of x here. What would we say about this? Well, we can say that this would be, our first term is x, and this would be 1 minus negative x. And so here, what we can also say is, all right, this is this previous series that we just had, but our first term is now going to be x, and we're multiplying all of our previous terms by negative x to get the next term. So minus x squared plus x cubed minus x to the 4th, and so on. Okay, go ahead and try h of x on your own. So if you had an opportunity to try that, hopefully you got that this would be equal to x squared minus x to the 4th plus x to the 6th minus x to the 8th. Now I get that you might not be seeing the full benefit of representing a function as a series just yet, because quite honestly, we haven't really done any calculus yet. So let's get to that. Let's actually do some calculus involving power series and see their connections with doing the calculus of the function itself. So let's start with 1 over 1 plus x squared. So asking ourselves the following: what is the derivative of 1 over 1 plus x squared? Well, those of you who know me know that we're going to have to likely use the quotient rule here. And not a huge fan of the quotient rule. It's totally important, but let's be honest, it's not always the most fun thing to do. But after doing the quotient rule, let's see, that would just be 0 minus, we got negative 2x, and then we just need to square that denominator. And that. Fortunately, that wasn't too bad. Now, we had the derivative of this, which I want to just highlight for you here. But let's look at the following. What would be the series to represent this function 1 over 1 plus x squared? So let me take this particular function and let me just rewrite it so it's a over 1 minus r. So 1 over 1 minus negative x squared. So we know that then this is equal to the following series in summation form. So n is equal to 0, infinity. Our first term is 1, and our common ratio is negative x squared. And so we're raising that to the n power. Okay? So with the tools that we have, we would not be able to create a geometric power series for this function of f prime of x, right? Because right now, there's really no way for us to rewrite this denominator, so it's just simply 1 minus our common ratio r. However, since we know the power series for our original function f of x, and we know that for the interval of convergence, this power series is the function, we can then differentiate the power series for f of x to get the power series for f prime of x, which I think is super cool. So the derivative of the general term of f of x will be equal to the general form of f prime of x. So let's look at the power series of f of x. Let's actually just write out the terms. So f of x here would be equal to the following. Our first term is 1, and then our next term is negative x, or excuse me, x squared, plus x to the 4th, minus x to the 6th, plus x to the 8th. And this would just continue, okay? Now, if I wanted to try to come up with a power series for f prime of x, again, if I wanted to look at this and try to come up with a power series just by looking at this function, we don't have the tools right now to be able to do that. But what we just observed was, hey, if this function here is the derivative of this function, that means the derivative of this series here would be simply this power series for f prime of x. So let's just differentiate each term. We've got 0 for the first term. The next term would be negative 2x plus 4x cubed minus 6x to the 5th plus 8x to the 7th, and this would continue, right? So differentiating the power series gives us the power series of the derivative of the original function, okay? Well, what about the original term, or excuse me, the general term, I should say? We can say that the derivative of our general term of a sub n is, let's just write this, the derivative of, what do we say our a sub n was? This was negative x squared to the n. Well, if I would differentiate that using the power rule, I would say this is n times negative x squared to the n minus 1. And then using the chain rule, we write minus 2x here. And let's just clean this up a little bit. We would say this is equal to negative 2nx, negative x squared to the n minus 1, right? So differentiating the general term, our a sub n, gives us the derivative, or excuse me, the general term for our derivative, our f prime of x here, okay? And to really highlight one of the cool powers of this, no pun intended, let's look at the following power series here of f of x. And let's determine the derivative. And let's see if we can use the derivative to give us information about what we think the function itself might be. So by just looking at the power series right now, it might be a little bit difficult to determine what our common ratio, if any, might be. So looking at this series right now, it's not super clear to us what f of x is, what our original function is. And the reason for that is because that original function actually won't be a rational function, but I'm getting ahead of myself. All right, So instead, let's look at the derivative of this series to see if it gives us any clues. So I'm going to do that by just looking at the derivative of each term. So this first term would be, we got 0, and the next term after that is 1. This next term would be 2x over 2 factorial. This one would be 3x squared over 3 factorial. And I'm going to just keep doing this over 4 factorial. I'm going to keep doing this. And then with the general term, again, applying the power rule here, we've got n times x to the n minus 1 over n factorial. And just kind of compare to make our general term with what's going on with it in our series, just to make sure it works. Should note that this is if n is equal to 0. We're starting with n is equal to 0. Okay, and this series is just going to continue there. All right, so we've just come up with our series for our derivative. And it may not be super clear to us right now, so let me go ahead and actually simplify this here. This is going to give us 1 plus, we've got 2x over 2 factorial becomes x, plus x squared over 2 factorial. And you know what? I'm going to bring that 0 down because I think that might help us. Well, actually, let's just leave it as it is. Plus x cubed over 3 factorial plus, and if I bring all this down, and this general term that we have here, I'm going to simplify that. This is the same thing as the following, x to the n minus 1. And if I divide that n into n factorial, I'm left with n minus 1 factorial. Now, take a look at this series for the derivative. See if you notice anything about it. Specifically, compare it to the original series that we had for f of x. And based on this, can you figure out what the function is? If you can pause the video right now, think about it. Well, hopefully you've had a chance to think about it. And if you have, then hopefully you had this very cool light bulb moment. Did you guess what f of x is? It is e to the x. And how did I know that it was e to the x? Because this series that we have here is simply the same series as itself. In other words, the derivative, the power series for the derivative is exactly the same as the power series for the original function itself. Although it looks a little bit different here, that's simply with us starting at n is equal to 1, and the original series with us starting at n is equal to 0. But they're the same exact series. And what's the function that we know whose derivative is exactly equal to itself? It's e to the x. It's the same thing as the series for f prime of x, which I think is pretty neat. I want to finish up this video by just talking about the integration with power series. So we just talked about finding the derivatives of power series to give us some information about the derivative of the functions, or vice versa. Well, we can also integrate power series to help us find new function series representations. So for example, let's start with this integral. The integral of 1 over 1 plus x dx. Well, this isn't too bad. That's simply the natural log of the absolute value of 1 plus x plus some constant c. Well, what does the series for 1 over 1 plus x look like? And we did that a little bit earlier, so it looks just like that, 1 minus x plus x squared and so on. And we know that this function is exactly equal to this series when the absolute value of x is less than 1. Now we're going to use this bit of information to find the series representation of the natural log of 1 plus x. Well, what do I mean by that? Since I know that this integrand results in this power series, and I know that this is the integral of 1 over 1 plus x, that must mean that the power series for the natural log of 1 plus x must be equal to the integral of the power series of 1 over 1 plus x. So I can say the following, that if I integrate each one of these terms that's in this particular series, if I integrate each term, I'm going to get the power series for the natural log of 1 plus x. So we're going to write the following. We've got x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4, and so on. Well, I need to solve for c, and I'm just going to use that x is equal to 0 to solve for c. So if I just plug in natural log of 1 plus 0 here, and substitute 0 for x, that means all of the preceding terms are going to become 0. And so we can just say that this is 0 plus c. So that means c is just simply going to be equal to the natural log of 1, which is just, oops, maybe don't cross that out, which is equal to 0. So that constant is effectively just 0. So with this bit of information, see if you can write the series for the natural log of just x. So pause this video and see if you can work that out on your own. Well, in order for us to write the power series for the natural log of x, we had to think about this argument in terms of this argument up here. Well, this is simply the same as the natural log of -1 plus 1 plus x, if you will, right? It's simply the previous argument minus 1. So all that means for us is we're going to take the same series that we had before, and let me just change this color here. We're going to take the same series that we had before. Oops. There we go. All right, we're going to take the same series that we had before, and we're just going to replace every single one of our arguments with x minus 1. And again, I got x minus 1 by just simplifying here. This would be the same thing as 1 plus x minus 1 if we just rearrange those terms. So I'm going to take each one of these variables here and replace them with x minus 1, because now I can treat this as like my u, and this is my argument here, u. So now we have the same series, and we're just replacing all of our u's now with x minus 1. So this would then become x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus x minus 1 to the fourth over 4, and so on. All right. So again, just to recap, we talked a little bit about the calculus of power series and understanding that we can do the calculus to the power series itself in place of doing the calculus to the actual function. And this is going to have a lot more benefits and implications for us as we move forward.